Okay, okay. Welcome now to the last part of chapter 3, and this time we'll talk about isosceles triangles. So recall that we already have defined what an isosceles triangle is, and we know that an isosceles triangle is a triangle with two congruent sides. So let's illustrate that first. Okay, and let's name this triangle as triangle JAN. And we know that since this triangle is an isosceles triangle, then it has two congruent parts. Okay, or two congruent sides. So if, say for example, if we have a triangle JAN is an isosceles triangle, then what can we conclude is that side or segment JA is congruent to segment MA. Okay, and the reason for that is the definition of an isosceles triangle. Okay, so since we are talking about isosceles triangle, it's so fascinating that there are also theories and there are also explorations on this type of triangle. But before we proceed to the explorations about this triangle, let's have first the parts of the isosceles triangle. And basically, if we have an isosceles triangle, the first part that we have to be reminded of is the vertical angle or the vertex angle. The vertex angle. And in the given illustration, the vertex angle is angle A. Next, we also have the legs. And the legs of the isosceles triangle are segment JA and segment MA. We also have the base of the isosceles triangle, which is segment JN. And finally, we have the base angles, which is angle J and angle N. Okay? So those are the parts of the isosceles triangle. Now, let us define first some important concepts, particularly will be helpful in proving theorems on isosceles triangles. So let's talk about the median of a triangle. The median of a triangle is a line segment that connects one vertex of a given triangle to the midpoint of a side opposite that vertex. So if we are given this figure, notice that the median says that it will start from the vertex of a given triangle to the midpoint, okay, of the side that is opposite to the vertex. So in this particular example, A is the vertex, and then the side opposite to the vertex is segment BC. And to name that the midpoint of segment BC is point M. So given that AM is the median of triangle ABC. So what we can conclude, if AM is the median of ABC, then we can say that the median of a triangle acts as a bisector. Okay, it acts like a bisector because it has to pass through the midpoint of the side that is opposite the vertex. But again, it is not the bisector of a segment. Okay, so if that's a bisector, if the median of a triangle acts like a bisector, and since the bisector passes through the midpoint, we know that the side that is opposite to the vertex of the triangle, then it divides that side into two congruent segments. So therefore, we say that BM is congruent to segment MC. Okay, and that is because of the definition of a median of a triangle. Okay, another important concept is the idea of perpendicular bisector. Okay, and then we know that when we talk about perpendiculars, we know that there is an existence of a right triangle. So an existence of a right triangle. Okay, and the existence of bisector is that it must pass through the midpoint and it will divide the segment into two congruent segments. So the perpendicular bisector of a triangle is a line that is perpendicular to one side of a triangle and through the point of that side. So if we are to illustrate that, this is the illustration of the perpendicular bisector. And the perpendicular bisector of triangle ABC is line FM. So given that FM or line FM is a perpendicular bisector. Okay, perpendicular bisector. So we can conclude that number one, of course, we know that we can conclude that triangle FMC and triangle, it should be angle, and angle FMB are right angles. That's the first one. And the second conclusion is that segment BM is congruent to segment MC. Okay, and the reason for this is definition of perpendicular bisectors. Okay, also we will talk about the altitude. Okay, the altitude of a triangle, and the altitude is actually the height. Okay, it's synonymous to the height of the triangle. It is a line segment that is drawn from a vertex that is perpendicular to a side opposite that vertex. So we can see here that the altitude seems to be a median of a triangle, but it does not pass to the midpoint of the side opposite the vertex. Okay, but it borrows the idea of perpendicular bisectors in such a way that the altitude is perpendicular to the side that is opposite to a given vertex. So, to illustrate that, we'll have this figure, and we know that according to our definition, that segment AE here, or line AE, is actually the altitude. Okay, as you can see that it came from vertex A, okay, down to the side that is opposite to this vertex. Okay, that is one property of the median. It must originate from one vertex. But again, it does not have to pass through the midpoint of segment BC. Okay, and it borrows actually the idea of the perpendicular bisector in such a way that this segment must be perpendicular to this side, opposite to this vertex. But again, it does not pass through the midpoint of segment BC. Okay, that's the altitude. Those are actually terms that are interrelated to each other. So, given that segment AE is the altitude of triangle ABC. So what can we conclude? We can conclude that AE is perpendicular to segment BC. Okay? According to our definition. And that is the definition of an altitude. Okay? An altitude of a triangle. Okay? So each triangle has three altitudes, one from each vertex, and based on our figure as shown for triangle ABC in figure 3.27, okay, this figure, the three altitudes seem to meet at a common point. Okay, we call it concurrent. Could also have an altitude that is outside the circle. It could be. Now, let's have a theorem. It says here that the corresponding altitudes of congruent triangles are congruent. Okay, so we need to show that is true, but first let us illustrate our triangles. Let's have two triangles first. And let's name this one as triangle A, B, C. And let's draw the altitude, which is segment BD. Okay. And then let's have another triangle. Let's name this one as triangle RTU. And let's draw an altitude. And let's name this one as segment TP. Okay? And let's say that let's provide a congruent part. Let's say segment AB is congruent to segment RT, and segment rather angle A is congruent to angle R. Okay, so according to this, if triangle ABC is congruent to triangle RTU, and segment PD and TP are altitudes, then let's show that segment BD rather is congruent to segment TP. Okay? Let's have our proof. Let's have our statements and our reasons. Okay, for number 1, we know that we can get something from the second given, which is segment BD and segment TP are altitudes. That is given. So since we know that they are altitudes, according to our definition is that it should be perpendicular to the side opposite to the vertex. So we say that the PD is perpendicular to AC, and segment TP is perpendicular to segment RU. And this is by definition of an altitude. Okay. Now, since we know that BD is perpendicular to AC and TP is perpendicular to RU, we can say that angle BDA and angle TPR are right angles. Okay, and that is the definition of perpendicular lines. Okay, number 4, since we know that they are right angles, we can also say that angle BDA is congruent to angle TPR, and that is all or any two right angles are congruent. Okay, so we are done with the information coming from our first given. Let's now talk about our second given, which is angle ABC, triangle ABC is congruent to triangle RTU. Okay, this one is given. And if angle ABC is congruent to angle RTU, we can say that angle A is congruent to angle R. Okay, angle A is congruent to angle R, as well as segment AB is congruent to segment RT. Segment AB is congruent to segment RT, and that is CPCTC. Corresponding parts of congruent triangles are congruent. And number 7, we have already shown that they are true, they are congruent, and this one is, we can say that triangle BDA BDA is congruent to triangle TPR. Okay? TPR. TPR. And this is because we have actually a hypotenuse and an acute adjacent angle. And we have a theorem for that, and that is HYA. Okay? Congruence theorem. Okay? And number 8. So then, since these are already true, then we can now say that BD is congruent to segment TP. And that is because of CPCTC. Okay? And we're able to show that the theorem holds.